Good afternoon.
Good afternoon. Good afternoon. Hope all is well. Trying to get these kids quiet before I had unmuted. Hope everybody's doing all right. Let's see. Everybody in here? Looks like it. So, like I said, good afternoon. Hope everybody's doing great. Hope everybody's doing all right. Um, look, we got knockout today, and we'll be off into the weekend, right? Let's see. This is yep, yep, yep. Yep, get ready to get our weekend started. Any general questions before I get into anything? Everybody all right? Anybody have any questions? So don't forget last class we covered all of chapter 3. Trying to check something real quick. Mm-mm-mm. So we're looking to jump into chapter 4 today. But I was checking something in my math lab real quick before we get rolling. Yeah, just a thought. Okay, so today, I'm not going to fill up the whole time. I was looking and I thought that's what I remember seeing that some of us need some time to get caught up. But unfortunately, when you're talking about summer and the 10-week session, we don't really have the luxury to not do anything. So we'll at least do 4-1 today, and you know, you guys take advantage of the weekend. Make sure we use our time wisely. You don't want this stuff to be you know too massive of an amount of stuff to get caught up on. You want to, make sure we progressively knocking this stuff out as we go throughout the course. So,
Can we use the easycalculation.com during the test?
yep,
Okay. Because
yep.
they have a number summary thing
hmm
too. So,
yeah. Easycalculation.com. If you fully explore their website, which I haven't even done, they have a lot of stuff, to offer. So that's why I always shoot people there. And normally it's okay. Maybe leaving. No, when I say reliable, not okay. Normally their stuff is reliable. Whereas some stuff you can find some stuff out there they'll calculate stuff. You be like, where did they get that from? But easycalculation.com normally is reliable. Refuse to vacate. All right, not a problem. Not a problem at all. Sorry, somebody said something in the chat, so I had to, want to make sure we're good on that. All right, so like I said, we'll look at 4-1 today. It's more of terminology anyway when you look at 4-1. I think it's some minor calculations at the end. But let's get you guys in here and out, and we'll be good to go. And so, yeah, no, y'all don't need to see that because we're not doing the assignments. All right, so 4.1 scatter diagrams and correlation. Scatter diagram is just a graph that shows the relationship between two quantitative variables measured on the same individual. And that makes more sense once you put some numbers on it in the application. So you'll see what I mean in a second. All right. Each individual in the data set is represented by a point, and those points are created by an explanatory variable and a response variable. We'll talk about the differences between those two in a second. I'll just give you guys a chance to write that down. All right. Don't go too far. Let me know.
Are they only two? Could it be more than one variable or just two?
No, it's just those two. Like X and Y, like when you plot on the XY chart. Yep.
Right.
hmm Just those two. So your explanatory variable will explain the value of the response variable. And your response variable is explained by the explanatory variable. In other words, it responds to what happens in the explanatory variable. So in other words, you'll see when we get to one example, um, you have a golfer, and the explanatory variable is how fast he swings the club or how hard he swings his club, and the response is how far the ball travels. So that's the difference between the explanatory variable and the response variable. Let's see, somebody says something in the chat. All right, give me 1 second. So I don't know how far you need me to go up. Let me know if you need to go up for a little further. So your explanatory variable will be your X, response variable will be your Y. Your explanatory variable will be your domain, response will be your range. These are just different ways of categorizing your explanatory versus your response. Then we have your input versus output, independent versus dependent. Got a few more, but I know somebody told me to scroll up. Are we good on that front? Did I scroll up enough? So I don't know if silence is good, I guess. All right, so then, okay, here we go. Okay, cool. And so the last part of that, your horizontal axis, if we're talking about X, we're talking about your horizontal axis, Y is your vertical axis. And then also when we get down to, that'll be more so 4.2, we'll see how our explanatory variable is our predictor, and our response will be what we predict, the predicted. All right, scrolling up a little. And right here, just generically, is what a scatter plot would look like. All you're using is the first quadrant. For those who remember back in algebra, when you had the graph on the XY plane, Cartesian coordinate plane, you have 4 quadrants. We're just using the first quadrant. Notice your horizontal axis is your explanatory variable, your response variable will be the vertical axis. And then you'll have these points that you will plot that will represent each observation. Let's scroll up. Anybody still copying? All right, next thing is linear relations. When a line best sums up the shape of the scatter plot. So there's not normally a red line. I just use the red line just to signify, which scatter plots are linear versus non-linear. So we see our first two are linear because a line best sums up the pattern. The next two are non-linear. We have like an arc in the third one, and then the fourth one is more like a wave. And then the last one is no relation at all. All right, down in the purple, nonlinear does not mean no relation, just means no linear relation. And that's what I was trying to show you with those diagrams. All right, you're still copying that. All right, so associations or trends, if it's positively associated or there's a positive trend, in other words, when one value increases, the other increases. So in other words, reading from left to right, your observations go up. If it's negatively associated, when one value increases, the other one decreases. So going from left to right, if your values go down, that's considered a negative association.
Can I ask a question about positive association?
Yes.
If a value, if one value decreases and that causes the other value to decrease, would that also be positive?
No. So we wouldn't be doing that. So when we're talking about one value increases, we're talking about, remember, we're only dealing in the first quadrant. So it's really no such thing as your X decreasing. You know what I mean? That means you would go in actually into the second quadrant. So it's all about increasing because your X values are positive and they're going in the right. So in other words, as your points go to the right, are your Y, as X goes to the right, are your Y's going up or are your Y's going down? So and then also all of your Y's are going to be positive. So notice we're not going. So if you go to your your four quadrants, we're only dealing with positive values. So none of our values will be negative. And so we're talking about going in this direction, and your Y's are either going to start up here and go down, or they're down here and they're going to head up. And so those are the only type of value. Because when we talk about measurements, there's no such thing as a negative measurement anyway. So that's why we don't even deal with, when we talking about this stuff, we don't even deal with negative, the other quadrants, because the other quadrants pull in negative values. Hopefully that answered your question.
Yeah, that answered it perfectly. Thanks.
Okay. All right, everybody good with that before we look at the linear correlation coefficient? All right. So your linear correlation coefficient, a measure of strength and direction of the linear relation between two quantitative variables. Sorry about that. Remember we talked about how certain symbols are for your population and certain symbols are for your sample. Greek letter rho is for our population correlation coefficient, and the letter R is for our sample correlation coefficient. Notice in the red, I mentioned right here that we will be using R. So we will always be using our sample correlation coefficient. All right, everybody good if I scroll up?
Professor, what is the letters that's encircled in the purple?
Rho?
Oh, RHO, okay.
Yeah, rho. I'm sorry, I could have said RHO, but yeah, just rho. That's Greek letter. That's how you say it. That's the Greek letter rho. It looks like kind of like a P for us, but it's really not a P. It's rho. And
Okay.
and I just put that in there just in case my math lab would have asked you, I don't know, some type of concept question, but we're actually going to use R for our correlation coefficient.
Oh, that's what you're saying. Okay,
Mhm.
thank you.
Mhm. All right, everybody good? All right, so in the blue, very similarly to when we talked to you guys about standard deviation and your variance, you want to find a calculator, website, app, something of that nature that can produce the correlation coefficient and your regression line. Those 4.1. Oh, still have my eraser up. Sorry. So 4.1 is the correlation coefficient. That's the section we're in right now. 4.2 is what we'll talk about next class, which is your regression line. Once again, easycalculation.com. If you do correlation coefficient, easy calculator or easy calculation, the first one that pops up will be that. Same thing with regression line. If you type in regression line, easy calculation, first link will pop up there. And like I said, the only reason I always say them is because I've used them before and I know that easycalculation.com works. But you don't have to use it. You can use whatever you like. As long as you're producing the correct answer, you should be good to go. Any problems? All right, so let's look at the properties, some properties of the correlation coefficient. So the first one is it's in between 1 and 0, -1 and 1. Where did I get 1 and 0? It's in between -1 and 1, and that's inclusive. So it is possible for it to be -1. It's possible for it to be +1. If R is +1, then a perfect positive linear relation exists. If R is -1, then a perfect negative linear relation exists. And I'll show you, what that means in a second. The closer R, looking at number 4, the closer R is to +1, the stronger the evidence of a positive association. The closer R is to -1, the stronger the evidence of a negative association. Oh, somebody said something in the chat. All right, how far you want me to go up? Or did you need?
Right there is fine.
Okay, cool.
I just have to see the chart a little bit.
Yep, not a problem. All right, scrolling up a little. All right, number 6, if R is close to 0, then little or no evidence exists of a linear relation. So in the red, just re-emphasizing what that means. R being close to 0 does not imply no relation, just no linear relation. So notice it says linear relation that we're focusing on. Remember, we also had, the arc and the wave. There's still a relation, it's just not linear. right. Any problems? Everybody good? I think that's it right there for our properties. Number 7, it is a unitless measure of association. And then 8, it is not resistant. It is affected by outliers. So we talked about that before. If outliers do affect your correlation coefficient. All right. If I scroll up too far, let me know. So first 3 generically. Generic, what do they call it? Scatter plots. Okay, not a problem. Not a problem at all. So that perfect positive linear association, R is equal to 1. It's right here, it's just a straight line. But then the further you deviate from that straight line, or the further your data points spread, the further start to move away from 1 and start to move closer to 0. And so that's what happens with the 0.9, and then you see the 0.4 is even more spread. Then the -1, same things. Perfect line, but it's going down when you read it from left to right. And then once again, if you talk about negative, it begins to spread and go away from that perfect line towards 0. And so that's what happened with the -0.9. And the same thing would occur with a -0.2 or -0.4, -0.3. It would all be still going down, but it would be further and further away from being a perfect line, perfect straight line. Then the last 2 are examples of being close to 0, or being close to 0. In that next to last one, notice there is a relation. It's just not a linear relation. Remember, this is only for linear relations. And then, of course, there's no relation in that last one.
I'm sorry, Professor. I'm in the car right now, but could you explain 0.4, please? 0.4.
Now, this is generic. Now, you're going to plug values into, like I said, Easycalculationcom and get this number. That, I've just put some points up there and just give you an example of how something would look as it moves further and further away from a straight line. So, like I said, that's just a generic example of what it would look like. You will have numbers that will produce, these numbers, and just basically the number that you get as your correlation coefficient as R actually lets you know how strong of an association it is. The closer it is to 1, the closer it is to a straight line. That's why 0.9 is closer than 0.4. There's more spread in the data values of 0.4. And so that's all he's saying. The closer it is to 1, the closer it is to a perfect straight line. The closer it is to 0, the further and further it is away from that straight line. So hopefully that answered your question about 0.4. All right. Anything else before we scroll up? All right. Everybody still copying? Can I go all the way up? All right. Everybody good with that? Don't want to start talking then. Somebody said scroll. Everybody good. Okay. All right. So I think this is the last thing of this section. Let me see. Yep, that's the last thing. Then, like I said, I'll let you guys go after this, and we'll look to do 4.2, 4.3 next class. So testing for a linear relation. So first step, and we're trying to make sure that we legit have enough information that says we have a linear relation. Remember, that's what we're looking for. First step is to determine the absolute value of the correlation coefficient. So we want to find it. And really, you got to find correlation coefficient first, right? But then you're going to determine the absolute value of it. Then we're going to find the critical value from table 2 in appendix A. I left out table 2, but we're looking at table 2 in appendix A for the given sample size. And I'll pull it up, show you what it looks like. That's in the back of your book in your appendix A, table 2. If the absolute value of the correlation coefficient is greater than the critical value, a linear relation exists between the two variables. Otherwise, no linear relation exists. So just give you guys a chance to copy that. As a matter of fact, while you guys do that.
So in step 2, that says find the critical value from appendix A, which is referencing something in the textbook.
Yeah, it's table 2 in appendix A.
Okay, thanks.
Let's see, where's my book? All right, is everybody done copying this?
Not yet.
Okay, not a problem. All right, just scrolling up a little. So this problem asks us to determine whether a linear relation exists between the club head speed and the distance. So once again, we have a golfer. And we're talking about how fast he swings his club, which you assume that's how hard he's squeezing it. I said squeezing it, swinging it. And then the response variable the response to him swinging the club harder will be how, or swinging the club at any type of speed will be how far the ball travels. Let me see something. Yep. So take a picture of these so I can transfer them. We have 100, 257, 102, 264, 103, 274, 101, 266, 105, 277, 100, 263, 99, 258, 105, 275. So basically what it's saying is in that first one, when he swings the club when he swung the club at 100 miles per hour, the ball went 257 yards. Then when he swung the club at 102 miles per hour, the ball went 264 yards, and so on. So keep in mind that these are not 18 different, not 18, these are not 16 different observations, they are 8. You know, this one right here is one observation by itself, and then 102, 264 is another observation. So that's 8 observations. He swung the club 8 different times, and those were the results. All right, anybody still copying the table? So we can go to the next thing, actually find the correlation coefficient. All right, so I'll go to Google, type in correlation. Oh, already got it there. Correlation coefficient, easy calculator or easy calculation. And the first one to pop up is easycalculation.com. All right, so you see you can add rows, take them away. So you need 8 of them. So we got 100, 257, 102. All right, so those are our values. And so 8 total numbers and then our correlation. So make sure in my math lab you pay attention to how many decimal places they want, whether they want 3 or 4, and make sure you round accordingly. Also, make sure you pay attention to your data values. Make sure you recheck them, because notice right here, let's say if I go from 275 and I make a mistake and hit 276, that changes the whole number. So it's 0.944444 now. So that one digit changes everything. So you always want to make sure that you go back and recheck all of your values. So questions on that before we go any further, make sure we're good. All right, so let's go back to the notes. So first thing I did was found the correlation coefficient. That's what we just did right there. I did 3 values, must have did 3 values because that's what my math lab asked about. You know, I probably did it that way. Normally I do 4 values, but my math lab must have said 3. All right. So now you take the absolute value of your correlation coefficient. So remember, your correlation coefficient can be positive or negative. Absolute value ensures that we're just looking at the positive result. So in other words, if I had, R equal to negative 0.567, absolute value of that is going to be 0.567. We just want the positive representation of that number. Absolute value, if you apply the absolute value to a positive number, the number is positive. If you apply the absolute value to a negative number, the number is still positive. So that's why I was emphasizing right here. Absolute value of 3 is 3. Absolute value of negative 3 is still 3. Questions on step 2. All right, so find the critical value from table 2 in appendix A. And notice I gave you the page number. That's page A2, A-2. So let's go to it. Well, I'll give you a chance to write that down first. I'll write down that. All right, so go to the e-text. Notice right here, I typed in A-2. That's what I put over there in the notes. Page A-2 will bring you to that the chart. If you were to type in 3 right there, it'll take you to page 3. You type in 10, it'll take you to page 10. This page is A-2. Does somebody say something? Okay, all right.
Sorry, that was
Okay, not a problem, not a problem. I just wanted to make sure. So now we go to the number of observations. It's 8 for us. Remember I told you he swung the golf club 8 times. And we see the critical value that we have here is 0.707. All right, any problems with that part?
Would the critical value, is the critical value derived from the value, like calculated from the values of the club head speed and the distance, or is that like an inherent thing when you have 8 values?
Right. That's it right there. It has nothing to do with the club head speed or anything. It's just that if you have 8 values, then now they've done some background work that we don't have nothing to do with. You know what I mean? So how they got this chart is beyond this class. You know what I mean? So all we want to look at is how many observations do you have? So in other words, let's say if you are a doctor and you're measuring heights and age according to height. If you have 8 observations, your critical value is still going to be 0.707. So, yeah. So this has nothing to do with our observation, what we've done with the club head speed and all that. It's just about how many observations do you have? This is your critical value, 0.707. If we had 17 observations, then our critical value would be 0.482. All right. Any questions on this before we go back to our notes? Everybody good? All right, so that's where I got this bottom part right here in purple. N is equal to 8. Go to the chart. Critical value is 0.707. All right, so now step 4, we want to compare the absolute value of the correlation coefficient and the critical value. So remember our absolute value of our correlation coefficient was 0.939. When you compare them, you see that R is going to be greater than our critical value. So our conclusion is that since the absolute value of R is greater than our critical value, then a linear relation exists between the club head speed and the distance. So, you know, conversely, if R was less than the critical value, then no linear relation would exist. Any questions? Any questions? Oh yeah, this note. All right. Any questions, concerns, comments? Everybody good? Everybody straight? All right. So it's only 144. Like I said before, take advantage of the fact that I'm not hitting you, you know, with a whole bunch of information from 1 to 3. And so use this time to get caught up. Use this time to get caught up. Make sure you're in a good place coming into Monday. And so we'll, because really Monday we'll do 4.2 and 4.3, and then that'll be it for chapter 4. All right. So any questions or concerns, comments before we close out today? Very good. Everybody straight. All right. So everybody take care. Have a great weekend. Be safe. Somebody unmute. Was that something? Okay. All right. If not, have a great weekend. Be safe. You guys have a good one. And I will see you next class.
Thank you.
All right,
You as
thank
well,
you.
Professor.
Thank you. Appreciate it. Take care.
Thank you. Have a good weekend.
Thanks. You do the same.